Okay, so today we'll get to part 2 of this chapter 3, which is on the two-body motion and reduced mass. Okay, so what we have learned so far. So far we have learned how to find the orbit of a particle, right? So moving in a central force field. And the field, right? So in practice, we know that if we are talking about gravitation, we know that the central force field has to be provided by actually another mass, right? So just like the Earth orbiting around the sun, right? So, and in the previous case, so we have been just ignoring the motion of the sun, right, itself, right? So if we have this Earth orbiting around the sun, right? So because there's a force acting on the Earth by the sun, right? So that's why the Earth is orbiting like that, right? But on the other hand, right? So in principle, right? So the sun is also experiencing a force from the Earth, right? So that therefore, in principle, right? So the sun should also move a little bit, right? So in previous case, right? So we kind of just ignore that, right? So and that is for a good reason, right? So because we can say that for the example of the mass of the sun and Earth system, because of the fact that the sun is much more massive than the Earth, right? So then we can kind of just make an approximation saying that, okay, so the sun is fixed at one point, and it's just that the Earth is orbiting around it. Right? So that's we have been making such an approximation. Right? So, however, now let's consider a more general case. Right? So just imagine that you have two massive objects or two stars. Right? So they now have comparable masses. Right? So and this time, so again, they are exerting this gravitational force, right? So on each other, right? So but this time you cannot ignore the motion of any of them, right? So just like the picture I have over here, right? So I have this M1 and M2, right? So the forces are indicated by these two arrows, and both of them are doing motions. Okay. So this is what we are going to deal with today, right? So this is what I call a two-body motion. Okay. So at first sight, you might think that it could be a much more complicated problem, right? So because in the previous case, right, so we just consider this mass moving around this fixed point O, right? So but this time, as this one moves, right, imagine that the other has to also move, right? So that both of them move together. Okay. So, however, it turns out that mathematically, the problem is not really that complicated. Okay, so you can see that after I do the derivation, right? So you can see that all we have learned from the previous part of the chapter, okay, so can be again directly applied to this two-body motion, right? So it's just that we have to replace the mass of this one object here by the so-called reduced mass of the system. Okay. So then I'll show you how it works. Right. So here let's set up the vectors and the coordinate systems. Right. So now what we have here is, right, so these two masses over here, and let me again draw the two arrows to indicate the forces, right? So let's say, so we are still considering central force problem. So I call this F1, okay, and the other over here, F2. Right, so F1 is the force acted on M1 by M2, right? So and this F2 is the force acted on M2 by M1, right? So And of course, right, so in this picture, I'm drawing the case for the repulsive forces, right? So they repel each other, but you could imagine that you just reverse the direction of the two arrows, then it becomes attractive force. Okay. So this is the way that I set up the vector system, right? So what I have this time, okay, so is that this is the origin of the coordinate, which I call point O. Okay. So now, right, so in the previous case, we have the force pointing to this point O, okay, but not anymore, right? Because now neither of these masses are sitting at point O. Okay. But anyway, I need a point O, right? So to be the coordinate system. So now this R1, right? So and this R2 are the position vectors of the two particles or two masses respectively. Okay. And here I define one more vector R. Okay, so this is an important one. Okay, so this is the variable that we'll be using actually, as you'll see. This R, okay, so you can see from this picture, is the vector subtraction, right? So given by this R1 minus R2. So this is the vector. Okay, so this vector is basically pointing from one mass to the other. Okay, so finally, I have this capital R vector, which is the position vector of the center of mass of the system. Okay, the center of mass of M1 and M2. Okay, so here, let me just open a new slide, and then I want to use this picture again. So I'm just using the same picture over here. Okay, so now I'm going to start setting up my equations of motion. Okay. So what do we have here? So now this is the R vector, right? So I'm going to denote the unit vector R hat to be a vector that goes along the R vector. Okay, so like this. Okay, and actually let me just call the magnitude of R vector to be R. Okay, so now be careful, right? So this R hat vector, okay, so it's pointing like this, right? So it's not just like the polar coordinate we use, right? So in the polar coordinate we use in the last part of the chapter is this unit vector R is pointing out from the origin O, right? So this time it's not like that. But anyway, so now we are ready to write down the equation of motion. Okay, so let me say that, right? So the force, now let me just relabel the force over here. I just call it F of R hat. Okay. And the other force over here, right? So this one and this one is action and reaction. So of course, this one I just say this is minus F R hat. Okay. So now I have this equation of motion. First of all, for the first mass M1, so F equals ma, right? So M1 R1 double dot would be equals to this F of R hat, right? So and similarly, right? So for the other one, which I just have M2 R2 double dot equals, well, this time is minus f of r hat. So this is what I have over here. So and on the side, let me also write down something on the side, which are the, again, just to remind ourselves that this R is in fact the vector subtraction of this R1 minus R2. And also the center of mass, position vector of the center of mass, capital R, is this M1. This is just by definition, right? So I think you have learned this before, right? So this is just the definition of the center of mass, is this one. Right, this is something I have on the side. Okay, so let me just here, I can just rearrange it a little bit. So R1 double dot is just like 1 over M1 f of R hat. And this R2 double dot is this 1 over M2, so minus 1 over M2 f of R hat. Right. So now what I'm going to do is I have these two equations, and I'm going to try to find a differential equation, okay, for this R. So I have the differential equation for this R1 and R2. Okay, so it's actually easy to find a differential equation for this R1, right? So I just need to subtract the two equations. Okay, so that is this is 1, this is 2, right? So if I just do that, 1 minus 2, then what I have is the following, right? So that would be equals to 1 for M1. So this is minus, right? So this is plus 1 over M2 f of R hat. Okay. So, and here I will just write the following. So the left-hand side is just R, right? And then the right-hand side, what I'm going to call this is 1 over mu f of R hat. Okay. So that is, this 1 over mu is a new quantity that I defined. And this is the so-called the reduced mass that I was talking about. Okay, so here that means this 1 over mu is just defined as this 1 over M1 plus 1 over M2. And that means you can also write this mu as this M1, M2 divided by M1 plus M2. Okay. So this is how I define it. Okay. So now if you just look at this equation over here, okay, and mathematically, it's really the same as what we had in the previous part of the chapter, right? So in the previous part of the chapter, when we just have one mass, right? So we just have the following, okay. When we just have one mass in the central force field, this is what we have. And of course, at that time, okay, so this R is really talking about the position vector of that mass, okay. But here it's not really. It really is a vector pointing from one mass to the other, right? So, but up to this point, right? So you know that we can solve this equation, right? So because in the last part of the chapter, right? So we were able to solve this, right? At least for the case well, at least for the case when f of r is given by minus k divided by r squared. At least this is the case that we know how to solve, right? And that's why we can solve this problem over here. So then once we got, let's say once we are able to solve for r, okay. So but ultimately, right, so I do want to get the information of the position of this M1 and M2 individually, right? So actually that would also be easy, right? So because now you see these two vectors I have, right? So I have this R1, R2 are the two we want, right? So R now we know. Then if we also know this big R, okay, so you can imagine if we know this small r, and if we also know this big R, you'll be able to find R1 and R2 individually, right? So because if I just take these two equations, okay, so I'll be able to, okay, I'm running out of space, but if I take these two equations, I'll be able to say directly, say that this R1, I can express this R1 and R2 in terms of capital R and small r. It would be given by this. Right, so this is what I have. Okay, once you know small r and big R. Okay. And small r is solved by this equation. What about big R, this capital R? So the capital R is the center of mass of the system. So now if we treat these two body problems, but we just say that this is an isolated system, right? So there are no any external forces, then this R, this capital R itself is just a constant, right? Just a constant. And we can always choose our coordinate system, right? Such that the origin of the coordinate system is sitting at the position of the center of mass. So that is R is 0, right? So if you choose your coordinate system appropriately, right? So that is to say, right, so I can just cross this out. Once you find the small r, you'll be able to find R1 and R2 individually, right? Just multiplying your answer by this factor over here. Okay. So now you can see really we don't need to go through new mathematical derivation, right? So the way that so these two slides are just repeating what I had. But what we really do, right? So as I said, is that for particle in a central force, this is the equation of motion we solve, right? And then for two particles attracting or repulsing each other, right? So this two body problem, we also just need to solve the same one differential equation, right? Except that this m, the mass of the particle, is replaced by this reduced mass of the system. Okay. And then once you find R, right? So as I said, you just use these two equations to find R1 and R2 individually. Okay. So let's look at this reduced mass one more time, so a bit more to see its property. Okay. So suppose, right? So instead of calling this M1 and M2, let me this time just call this capital M and small m, right? Just to indicate that I am considering the situation where one mass is significantly larger than the other mass, right? So then in this case, right, so the reduced mass, right, as I define, is given by this small m times capital M divided by small m plus capital M, right? And it can be written as this, right? So, and if indeed I'm considering the case where capital M is much greater than small m, that is like the sun and the earth, right? So then that means this small m divided by big M is much smaller than 1. Then this reduced mass would be approximately equals to small m. So this justified, right? So the approximation we use, right? So if this is much greater than the other, right? So the reduced mass of the system is basically, right, approximately equals to the small mass of your system. So then here, right, so I don't need to give new practice problem in this case, because as I said, right, so you just replace the m by mu. Okay. But I do want to show you a few pictures, okay, to see how the orbit actually looks like, right? So these are some cases, right? So you could imagine that, right? So from this case, again, we will have 4 different types of orbits. So if I consider 1 over r squared, it's the circle, ellipse, parabola, and hyperbola. So then for the circle, so let me show you some examples. Okay. So I have 3 different cases. Okay. So where the systems, okay, so the ratio of the 2 masses are different. Okay, you can see from here, for example, if I have this m1 is 6 and m2 is 1, then I have this 2 to 1 is this one, and this 1 to 1 is this one. Okay. So what do we see over here, right? So you can see that. So let me again remind you one more time, how do I get the R1 and R2, right? So R1, again, let me write this right now one more time. Right. So now that this R, right? So this R as a function of theta, right? So I know that it can be written as this f of theta R. Right? So because of this minus sign, right? So you're easily to see that basically the 2 masses, right? So they are always kind of opposite to each other, right? So if you basically draw a line over here, right? So if you're looking to this side, you see one of the masses, and if you look back, you will see exactly the other masses behind you, right? So that's to say, right? So this mass is orbiting like this on this big circle, and then this small mass will be orbiting like this along the smaller circle. Okay, so right, so here I also indicate the arrows over here. And does it make sense, right? So if I have a big mass, right, so this one will give a very small circle, right? So but if their ratio are kind of closer, then the inner circle, the radius ratio between the 2 circles will becomes closer, right? So if I have exactly 1 to 1, right, so they are basically rotating around the common center over here. So then you could imagine, right? So if this is really big, if it is really big, then this blue circle, right? So will become very, very small. Okay, so small such that it just looks like it's not moving at all. Okay. So here's just a small exercise, okay, for you, give you 1 or 2 minutes. Is that can you find like the ratio of the kinetic energy, okay, for the two particles? Okay. So given M1 and M2, okay, so you can just express. So I expect you to express the answer, right? So in terms of the mass ratio. So it should be quite straightforward actually. So because first of all, right, so all you need to know is the ratio between the two radius. Okay. So here is R1, here is R2. So from this relation here, right? So I just care about the magnitude. Okay, so not really the direction over here. So you can conclude that the ratio R1 over R2, right, so it's given by M1 over M2, M2 over M1. And one thing, okay, so about the velocity, right? So the velocity, right? So if I just call this V1 and V2, right? So because I want to know the ratio of the kinetic energy, right? So I need to know the ratio of the velocities, right? So, but you know that because this is a circle, right? So we know that this V is of course given by this radius times the angular velocity. And clearly, right, so the angular velocity of these two particles will be the same, right? So once it complete one full cycle, one full circle, right? So the other one will also complete one full circle. Right. So that, in other words, right? So I can write down this V1 divided by V2 would be given by R1 divided by R2. So these are the two relations I need. So if I want to find out the ratio of the kinetic energy, right? So then what I need to do is just 1/2 M1, right? So R1 omega square divided by 1/2 M2 R2 omega square. So you can really work it out by yourself easily, right? So you just cancel the omega and then you just express this R1 divided by R2 also in terms of this M1 divided by M2. Okay. So similarly, if you want to find the ratio for the angular momentum, right? So you just need to know the following, right? So L1 divided by L2 would be this M1 R1 square omega divided by this M2 R2 square omega. So that's all you have for the two answers. So this is, of course, the most simple, easy case because we have this circular orbit, right? So, but of course, we can have elliptical orbits. Right? So again, I just show you some picture over here. Is that again, I have the different mass ratios, right? So you can see that intuitively, again, it's easy to understand, right? So the small mass will orbit in a big orbit, right? So the big mass will orbit in a small orbit, right? So again, you can see that if I have the mass ratio exactly 1:1, right? So I have the two ellipses looks like this. But one thing to notice that, right? So the two ellipses, they don't overlap in each other. Okay. So this is a short part of this chapter because, as you can see, right? So once you basically convert this two body motion, okay, into an effective one body motion, then you are done, right? So you just need to mathematically, you just need to replace the mass with the reduced mass of the system. Okay. Okay, so then we just simply move on to the next part of the chapter. Okay, so here we'll be talking about a concept that is so-called the stability. Okay. So from now on, I won't really be telling you whether I'm talking about a one body motion or two body motion, because as you have already seen, okay, so mathematically they are really the same. Okay, so and here, so just for ourselves to be to easy to visualize the problem, so I'll just again assume that this is just a one body problem where I have a fixed origin and a small mass. Okay, so this is what I'm going to consider again. Okay. So circular orbits. Well, circular orbits is the easy one to deal with, right? So for 1/r², so we have worked it out. And for other forces, right? So if I have this force to be this minus k divided by r², okay, so we completely solve it, right? So we understand all the orbits. Okay. However, we don't have a general method, right? So to deal with this general case, right? Suppose my force is minus k divided by r to the power n. Okay. So for example, if n is 10, okay, I don't know how to solve it. Okay, so or to be even more general, right? So I can say that f, right? So can be taking the form of any function of r, right? Right. So these two cases, oh, for sure, we don't have general method to solve. Okay. However, whenever we deal with circular orbits, right? So things are different. Okay. Why is that? Because whenever we deal with circular orbit, that means that we are fixing r value. Okay. And in that case, right? So then this force, at least this magnitude of the force, is not a variable. Okay, it's a constant only. Right. So then those we can deal with. So therefore, okay, so what we are going to consider is circular orbits. Okay, but it can be due to, okay, any of these kind of forces. Okay. And to be more specifically, I'll tell you whether the circular orbit is stable or not. Okay, so before we get into the general case, I'll again, okay, one more time remind you what happened for the 1/r². Okay, so remember this minus k over r², right? So if you want to find out, right? So the equation of motion for this circular motion, right? So I just basically have this, right? Centripetal force equals the attractive force, right? So, and from here, right, so I'm basically letting the angular momentum of the system to be L, right? So when I set up the problem, right, so let's say I have already give you the initial angular momentum L, right? So I should treat this L as a constant, right? So then you know that the radius, right, so of your circular orbit would be given by this L squared divided by MK, right? So this is something that we have seen before, right? So, and notice that, so what determines the radius of this orbit, right? That is, right, so the angular momentum of your system, okay? So if you give me a larger initial angular momentum, right? So the radius of this circular orbit will have to be larger. Okay, so you don't have that choice, right? So that give me angular momentum, then you need to follow this radius. Okay. So, and also remember the picture of the effective potential that I introduced last time, right? So this is the picture over here. Remember that if we are in the circular orbit, right? So the radius you are at is exactly at the point where the effective potential is at minimum. Right? So that is to say, right? So you can either just start with this equation of motion, or you can also look at the effective potential curve and find out this extreme point, right, or the minimum point in this case. Okay, so to look for the radius of the orbit. Okay, so then what do I mean by stability? Okay, so just imagine the following situation. Okay, so is that, okay, initially I already have this particle, okay, so moving around a circle like this. Okay, so as I mentioned a few minutes earlier, right, so the central force does not have to be 1/r squared, but the example that I just give is 1/r squared. But just imagine that this particle, right, so it's moving in this circular orbit, right, so due to a central force F(r). Okay. And if you don't apply any external perturbation, right, so don't disturb the system, well, you just go to the circle, you will just circle around the orbit over and over again, right? So now at some time, suppose you give an impulse, a small impulse, to this particle here, right, such that all of a sudden, right, so this particle is displaced a little bit like this. So you can see my small x distance here, right? So suddenly you just make this particle to be a little bit further away from the original orbit. Okay. So the question that I want to ask is the following. Okay, is that after you do such a perturbation, right? So what happened next? Okay, so will this particle start to fly away, right, further and further away, right? So just like this. Will it happen? So suppose it's moving like this, right? So will it goes like this? Just keep going away and go to infinity. Okay. Or so this is one scenario. Okay. Or it will kind of just after some time, okay, so it will go back to the original orbit. And in fact, here the term I use, the oscillate around the original orbit. Okay, it will be more clear what do I mean by oscillate around the original orbit. But just imagine something like this. So two scenarios. Okay, so which happens? Okay, so if it is the first scenario, okay, so I will say that this is an unstable orbit. Okay, So if this is the second scenario, I'll say that this is a stable orbit. Okay. So, right, so just imagine, right, so I have this circle. A stable circle orbit means that even I give some disturbance, okay, so it won't fly away indefinitely. So otherwise, this is unstable orbit. Okay. So if you just focus on thinking about this 1/r² problem, right? So actually, you might know the answer already, right? So because you know that, right? So always remember, right? So for 1/r², there are only four possible solutions, right? So circle, ellipse, parabola, and hyperbola. There are only the four possible solutions, right? So even you give some kick, right? So after you do that, you are still in the central force field, like 1/r². So that means, you know that after disturbance, okay, it might not be a circle anymore, but what choices do you have left? Ellipse, right? So or hyperbola or parabola, right? So, but because I told you already, so it's kind of a small disturbance. So that means I'm actually assuming that the energy that you give into the particle is actually small, right? So that is to say, you just imagine that originally, right? So your total energy of this particle, of course, is a negative number, right? So that's why you have this circle orbit, right? So if you give a little bit of impulse, okay, so just imagine that the total energy is still negative, right? So if that's the case, right, so you basically already know that you don't have choice, right? So but the new orbit must be kind of an ellipse, right? It cannot go to like a parabola or hyperbola suddenly, all of a sudden, because that would require a much larger energy. Okay, so to do that a change. Okay. So that is to say, right? So even I don't tell you anything else, right? So you know that this circle orbit should be kind of stable, right? So because from a circle, after giving some kick, maybe becomes an ellipse, but that ellipse does not make the particle go away indefinitely. Right? So, and indeed, that is the case. Okay, so but let's look at the same problem at a slightly different way. Okay, is that we are going to be looking at the effective potential curve. Okay, so we'll be looking at the effective potential curves a lot in this part of the chapter. So okay, so you have to make sure that you have a good understanding of this effective potential. Okay, so what happened is the following. Okay, so I'll finish this slide and then we'll take a break. Okay. So originally, as I said, if I look at the effective potential curve, okay, so I am at this position over here. Right? So this is the original radius of your particle. Right? So you apply a little bit of impulse, so to displace the particle a little bit. So if I look at the effective potential curve, so what it really means is that now you are maybe over here. Okay. So one assumption that I'm making here, okay, is that the impulse that I applied, okay, so does not change the angular momentum of your particle, right? So suppose the impulse I apply is along the radial direction. Okay, so and because of that, the effective potential curve that I have is still the same one. Okay, if the impulse that I applied will actually change the angular momentum of the system, then I actually cannot use the same effective potential curve, right? Because the effective potential itself depends on the angular momentum. Okay. But because I keep it fixed, so I can use the same curve. So now, right? So you are at this R prime, okay? So instead of R. Okay. So then the question is, so now you're at this R prime, okay? So what will happen? Will this particle under this effective potential, okay? So will this effective potential make this particle to go further and further away like this, or it will just drive back to this original position? So now that's the concept that I hope you still remember, right? So it's the relation between force and potential, right? So remember this force is given by this minus derivative of the potential, right? This is something you have learned before, I believe. Okay. And of course, now this is not the real potential, and this is not the real force, but this is the effective force, and this is the effective potential. Okay. So just now taking the derivative, right? So just means seeing the slope of this curve, right? So if you are at this green point, right? So what is the slope? If you are at this green point, the slope is positive, right? So this is minus du dr is negative. So that's why if you are here, the force, the effective force, will drive you back to the original point. Okay. Right. So this would be the direction of your F effective. And if you go back, you imagine that it will overshoot, right? So you might end up going over here. So now if you're at this point, the effective force this time will be in this direction. Okay. So actually from this picture, it's really easy to see. You just need to remember that, right? So the particle always want to go to the point where the potential energy is the lowest, right? So that's why if you are here, so you try to go to the position that is lowest, position where the potential is lowest. So that's why this green point will tend to move back here, right? So if you are here, right? So again, right? So it is looking for the point where the potential is minimum. So that's why it will goes like this. So that's why you imagine that in this graph, your particle will basically kind of oscillate like this. Okay. So, and that would be the oscillation that I talk about next. Okay, but not yet. Okay. So, but now let's take a 10 minutes break. Okay, so now it's 10:22. Let's come back at about 10:32. Okay. So what I will do after the break is to look at, as I said in the beginning of this part of the chapter, is other kind of forces. Okay, that does not depend on 1 over r squared. Right? Because 1 over r squared. Okay, so we know the answer already. Okay. Okay, so just now I have introduced the concept of stability, right? So and then we just start with the case that we are already familiar with, right? So that is the 1 over r squared, right? So but now we are going to consider some case that we are not so familiar with. Okay, so this is the next example here is that the force goes like 1 over r to the 4th. Okay, so this kind of force. Okay. So first of all, right? So I don't know how to solve for all kinds of different orbits under this force, right? So but it doesn't matter. So I just focus on the circular orbits. Okay. So how do I find the radius of this circular orbit? So again, I give you an initial momentum L. Okay, that's the thing that I give you. Okay, and then from there you tell me what is the radius of that circular orbit. Okay. So that again is easy. It's just that the equation of motion is the centripetal force, right? So equals central force. So that's what you have over here, right? So and then you'll be able to conclude that this R has to be equals to mk divided by L squared. Okay. Okay. So one thing to just to remind you a bit here is that so in the last case I have L squared divided by mk. So here I have mk divided by L squared. So it's just exactly the inverse. So you might wonder, what about the unit? Okay. Are the unit not consistent? It shouldn't be, right? So because this L squared divided by mk, okay, must have the unit of length, right? So here mk divided by L squared also must have the unit of length. Okay. So but it's exactly inverse. So how is that possible? Okay. So that is because of the fact that when I write down F equals minus K divided by L squared, K has unit, right? Has the unit such that K divided by L squared has the unit of force. So but when I say that F is given by K divided by L to the fourth, right? So K must have a different unit such that this K divided by L to the fourth give me force. Okay, so that means, okay, so just remind yourself, although we are always using the same symbol, but this K and this K, of course, they do not have the same unit. Okay. Remember that. Okay, but anyway, this we figure out. So this R has to be equals to this mk divided by L squared. Okay. So our goal is to study the stability, right? So now we will make use again the picture of the effective potential. Okay. So if you can see that the effective potential in this case, okay, so has a very different behavior compared to what we have over here, right? So why is that? So first of all, remember how the effective potential is constructed. It is the sum of two terms, right? The first term is the centrifugal terms, this one, and the second term is the real potential term, which is this curve over here, right? So so that means that the first term, right? So the first term is always looks the same, okay, which is this top dashed line over here, okay. But the difference is now the second term, the real potential, right? So if your F, your force goes like 1 over R to the fourth, then your potential must goes like 1 to R cubed. So here you can see that, right? So this is my 1 over R cubed, and this is my 1 over R. Okay. So because of this difference, if you add these two curves together, so this time you get a solid line that looks like this. Okay, so instead of this, that is, here I have a minimum point, but this time I have a maximum point. Okay, so in this case, if you have the circular orbit, so you will be again have to be at the stationary point of the effective potential, but this time it's over here, it's the maximum, not the minimum. Right? So now imagine you give the perturbation, right? So that is, you try to make the R to change a little bit over here. Okay, so this is R prime, right? So originally I have this R. So now look at this, right? So you can try to again, see the effective force, right? So, but without taking the derivative, again, you just have to picture that the particle will always try to roll down to the region where the effective potential is decreasing. Right? So therefore, once you displace the particle over here, then it must keep going like this, right? So go out indefinitely to infinity. So that clearly is unstable orbit, right? So on the other hand, you could imagine that if my initial displacement is not to the large side, but to this small side. Okay, so again, you can imagine that this has a really rapid drop over here. So then this particle will just keep going to smaller and smaller distance. Okay, and that is also an unstable orbit, right? So now you can see for 1 over r squared, we have stable circular orbit. Okay, so for 1 over r to the 4th, we have unstable circular orbit. Okay, so can we try to consider something even more general? So what about 1 to the 1 divided by r to the power 10? Okay, so let's say, so what about that? Or not 10, but 11, 12, and so on. So can we have a general conclusion? So then the trick you can see from this example and the previous example, the key is whether the stationary point here is a maximum point or a minimum point. Right, so that's the key difference. Okay. So then let's take a look at this general case. Right, so k divided by r to the power n. Okay. So again, as I said, I don't know how to solve for the general form of the orbit, but I just care about the minimum point of the effective potential. I can still write down the effective potential, right? So this is the effective potential that I can write down, right? So just verify by yourself, right? So if you know that, okay, so from potential to force, you take a derivative, right? So from force to potential, you do an integration, right? So to get there. But anyways, just remind you that, right? So this is the U, the real U, right? So the real potential. Just you can verify yourself that this is correct, right? So take the derivative of this, pick up a minus sign, you get to the force. Okay. So now this is the U effective, right? So I want to, so you can plot it by yourself, right? So, but you know that there's just a way to, without plotting, that we can find out the maximum or minimum point of this curve, right? So that is by taking derivatives, right? So first of all, let me find the radius of the circular orbit, right? So that is, we look for the stationary point of this U effective. Okay. So then if you take the first derivative and set it to 0, you will see that the radius has to satisfy this relation. Okay. So no any tricks here. Okay. Just try to take the derivative for yourself to verify. Okay. So, but the key is to find out whether this stationary point, right? So now we know that this is a stationary point, but we want to know whether this is a maximum or minimum point, right? So then, of course, what you do is to take the second order derivative, right? So if you actually take it and then substitute this value back to the expression, right? So you will be able to find that if you require the second order derivative to be greater than 0, right? Second order derivative to be greater than 0, that means a minimum point. That would require you to satisfy this inequality over here. Okay. And this inequality is actually, the result is quite very obvious because this L squared divided by M is just positive number, right? So that means this inequality gives n smaller than 3. Okay. So that is the general conclusion, is that a stable orbit exists for any n smaller than 3. And this verified the two examples that I just show you, right? So n equals 2, stable orbit, right? N equals 4, unstable orbit, right? So that agree with this general conclusion. Okay. So let's take one step further, is that now my force does not even have to follow this inverse power law. Okay, so I'll just say that for this f of r can be any function. Okay, can be any function. Okay, it can be, I'll have an example where it can be, for example, f of r can be something like this one. Right. So this is still a central force, but not power law. Right. Okay, so in that case, if the force can take any, no matter what kind of function you have, right? So the potential would be given by this one, this integral. Okay, so and the effective potential, I can again write down something like that. And what I'm going to do next, right? So it's just the exact same procedure, right? So taking the first order derivative, and then taking the second order derivative. Okay, so of course this time I cannot really exactly find the stationary point yet, right, without knowing the actual form of the force, right? So but let's say this dudr is equal 0 at some r naught. Okay, let me just say that. And then now if you want to have this circular orbit, right? So that means that this equations over here, this dudr has to be equals to 0, right? And that gives you a requirement for r naught, right? And you could imagine that sometimes maybe this one itself already not satisfied. Okay, but let's say we have just focus on the case where this equation 1 is satisfied, right? So if this is not even satisfied, then we don't even talk about circular orbit. Okay, but let's say that doesn't happen in our cases. Okay, so then with that, right? So if I'm going to take the second order derivatives, right? So then I have this expression over here, right? And then this L squared divided by MR naught fourth. Okay, so I can relate this with the FR naught itself. Okay. So then what I end up having is these two terms added together. Okay. So again, right? So I want the second order derivative to be greater than 0, right? So that means this whole thing to be greater than 0. Okay. And that is to say, I require, right? So let's just take the negative sign away. So I'm saying that these two terms added together has to be smaller than 0. So in order to have a stable circular orbit. So here, here is one exercise. Again, I'll give you 1 or 2 minutes to work it out. Okay. Okay, I understand that it might actually take you a bit more time to finish all the derivatives, but I just want you to understand the concept, right? So to know the method, right? So actually, this problem itself is quite straightforward, right? So all you need to know, right? So is to take the equations that we have just derived, right? So this one, and test, okay? So whether we can have this expression to be smaller than 0 or not. So one thing to be careful, right? So I am giving you the potential, but not the force, right? So then what you need to do first of all is to find the force, right? So let me write down the equation over here. Okay. Okay, so in this example, I'm calling the radius to be rho instead of r0. So our goal is to find this, right? So and see whether it's greater or smaller than 0. Okay. So then first of all, the f, you need to find out the first derivative of this potential. And I'll just write down the answer for you. So by the way, this problem is just one of the example problems in your textbook. So you can always go back to read it in details. But the first order derivatives would be this one. Okay. So, and it might take a bit work to actually work out the second order derivative, but let me just write down the answer over here. So we always have this exponential factor sticking to everything else. Oh, so by the way, so this kind of potential has a name which is known as the screened Coulomb potential. Okay, so perhaps you will see this kind of potential again if you learn more about atomic physics or scattering, but not going to really explain a lot here. But what you can see at least is the behavior of this potential. Okay, so what does it look like? So if you don't have this exponential factor over here, then you just have this minus k over r. So that is the pure Coulomb problem, right? So but now you are multiplying this minus k over r with another decaying function, right? So you know that this e to the minus r divided by a is a decaying function over r, right? So that is, it will be a function that is decay more rapidly compared to your regular Coulomb potential. So this is the behavior of the potential that I have over here. Okay. So now now I have f prime and this f, right? So and then all I need to do next is to apply this equation over here, right? So and after some simplification, you should be able to find out that this whole thing, if I want it to be right smaller than 0, so then what you have is the following. Okay. So and here you know that the exponential function itself is just always positive, so I don't need to consider that, right? So and at the end, so you find that the rho has to be smaller than some number. So there's some square root involved. So but I just write out the numerical value. Okay. So what it really means is that if your radius of your circular orbit, right, so is smaller than a certain value here, then that would be stable. Right? So otherwise, that would be unstable. Okay. So this A, okay, so what this A is actually over here, right? So this A is actually characterizing how fast, right? So this term decay. Okay. So if this A is small, so this would be rapidly decaying exponential function, right? So that means it's decay very, very fast. Okay. So, and in fact, right, so this is, if you have learned about exponential function before, you have seen this, you can call this the decay length, right? So, or when you learn about the exponential decay over time, you call this the decay constant, right? Something like that, right? So, but here really tells you that the radius cannot be too big, okay, for the circular orbit to be stable. Okay. So it's quite different from what we had with just the pure Coulomb potential, right? So the pure Coulomb potential, right? So the orbit, okay, is always stable, okay? So no matter what R you have, okay. So one thing to notice is that in this picture, right? So it seems that the R is fixed. The R is always fixed here. So how do I get to another circular orbit, right? So that is not at this position, okay. Right. So that requires you to actually change the angular momentum of your system, right? So because, as I said in the beginning, once you fix the angular momentum, you get one R, right? So if you want to get a bigger R, you need to give me a bigger L. And when you give me the bigger L, actually, the effective potential curve, the whole effective potential curve has already changed, right? So if you increase the L, right, so the potential curve should look something like maybe like this, right? So because this L's increase, so then at that time, then your new minimum point is over here, okay? So not here anymore. Okay, so that's pretty much all I need to say about the stability. Okay, and now there's next concept here is that suppose, okay, suppose I do have a stable orbit already. Okay, and then I also gave you the picture that just like a few slides earlier, right? So if I do have a stable orbit, so what happened is that if I displace the particle a little bit away, then the effective force will drive it back. And then if it's too small, and it will drive it back to larger position again. So you can see that here, this back and forth really looks like an oscillation, right? Really looks like an oscillation. Right? And now what I want to know is the so-called the oscillation period of this. Okay. So, but how the oscillation really convert back to the two-dimensional picture, right? So remember, this is not really a one-dimension problem, right? So when I say that R is fixed, it doesn't really mean that R is staying there. Instead, it's doing the circular motion. Right? So then, if I draw this picture to have these oscillations, that means I am still having kind of a circle, right? So, but at some point, the circle becomes larger and the other point becomes smaller, right? So then what happened is that, so don't look at the equation over here yet, but what happened that I'll show you is the following, right? So imagine that if you have just a circular orbit, no any disturbance, then you have this blue curve over here, right? So, and once you try to displace, suppose, right, so the particle was just happily moving in this orbit originally. But at this point, if you suddenly kick it over here, right? So what happens is that you have this small decrease in the radius, right? So but then as time goes on, you can see that it goes back to the original radius, okay? And then after more time, the radius become a little bit larger, and then go back to the equilibrium. So you can, that's what I mean by the radius of the circles, right? So of this, or the radial position of this particle, right? Sometimes getting a little bit closer, sometimes getting a little bit further away. Okay, so that's the picture that I want you to first have in mind. Okay. Okay, so now let's talk about the oscillation, right? So when you think about oscillation, right, so you will think of a simple harmonic oscillator, right? So remind you the simple harmonic oscillator, how the potential looks like, right? So the potential would looks like so let's say I have this mass spring system, right? So harmonic oscillator, right? So the potential and this position, right? So remember that the U is given by the U for the harmonic, a real harmonic oscillator, right? So it's given by 1/2 K x minus x naught square, right? So if you really have a simple harmonic oscillator, right, x naught is the natural length of your spring, right? So then the curve will looks like this, right? Quadratic curves that has this equilibrium position x naught. Okay, that's what you have for this simple harmonic oscillator. And now, if you compare this shape here, okay, with this one, well, of course, I cannot say that these two are the same, right? So they are not the same. But if you just look around this region, right? So this one looks like a bowl here. So this one also, right? So you can see just this part over here. So this part, right? So as long as I don't move this particle too far away, so if I just move it really around the minimum, right? So you could see that I can approximate this part of the potential curve as a simple harmonic potential, right? So maybe a curve like this. So approximate it like using this curve over here. Okay. So mathematically, so how it works, right? So mathematically, how it works is that we are going to use the Taylor expansion. Okay. So if I'm going to do the Taylor expansion of this U effective around the minimum point, right? So around the minimum point over here, right? So Taylor expansion, the first term is a constant term, right? The second term is with the first order derivative. The third term is the one with the second order derivatives. Okay, so now the first term is just constant, so don't worry about that. And the second term is 0, right? So because we are doing the Taylor expansion about this minimum point, right? So then the third term, you can see we have 1/2 times a constant times a quadratic term, right? So then you can see mathematically, right? So this term indeed, right, resemble the term for the potential for a simple harmonic oscillator over here, right? And you can see that this u, the second order derivative of u, it plays the role of your spring constant k, right? Let me draw that line again. And now, knowing the spring constant, so when you have this harmonic oscillator problem, so knowing the spring constant will then give you the frequency, right? So because remember that in the harmonic oscillator, the frequency is given by the square root k divided by m. So now, in this case, so that means that because the second order derivative plays the role of k, then the frequency of oscillation of my orbit is the square root of this second order derivative divided by m. Okay. So then let's do an example. Okay, so again, using the one that we are already familiar with, right? So I have this 1 over r squared, then this is the effective potential, right? So take the second order derivative, which we have done already, right? So this one, my second order derivative is this, and you substitute this r naught, right? This L squared back to here, then you will find that the second order derivative is given by this k divided by r naught cubed. Okay. Okay. So one thing, again, I use the same symbol, but remember, okay, remember this 1/2 kx squared is the spring constant k. Okay, so that 1k, but remember this k is not that spring constant k. Okay, so now the oscillation frequency omega is the square root of this one divided by m. So that's why I have this term over here, right? So this omega, remember, just using this formula over here. Okay, so then oscillation period is just 2 pi divided by omega. So this is it. Okay. So now I show you this picture already, right? So let me show you one more time again, right? So this is original circular orbit, right? So the oscillation means that, right? So the radial position sometimes getting smaller, and then sometimes go back to the equilibrium position. Sometimes the radial position is a bit larger than the original one, and so on. Okay. So then you can see that this is a displaced circle, right? Or in fact, this is a little bit like an ellipse. It is in fact approximately like an displaced ellipse, and that actually consistent to what we have learned already in the first part of the chapter, right? So for some particular energy, I have this circle, right? So you have slightly higher energy, it becomes an ellipse, and this is in fact, okay, approximately an ellipse. Okay, and now if we take a look at the oscillation period, okay, so look at this red curve over here. So what is the oscillation period? Okay, so the oscillation period is that, so let me just have more labels. So clearly here is the minimum, right? So let me call this our mean. And then as this particle move to over here, at this point, it go back to R naught. And as it keep moving up to here, then this is the R max. And another quarter cycle later, right, R naught again, and then R mean. Okay. So that is, right, so if I again draw the effective potential curve over here, right, so what did I just do? Okay, so that's not a very correct drawing over here, but let me. So what I described just now is that I go from R mean and then to R naught to R max. And then after that, I come back to R mean, right? So from R mean, R max, back to R mean. So as I finish one full orbit, I also finish one oscillation, right? So this so happened that the case, right? So that is the oscillation period is actually the same as the orbital period. Okay. So from here, you can actually find the oscillation period is this one. And if you go back to use what we have learned in the part 1 of this chapter, the Kepler's law, right? So you will also exactly find that the orbital period is also this. Right? So this result should not be surprising to you because otherwise things will be inconsistent. Okay, but it is really nice to appreciate that using another way of looking at this same problem, okay, gives you the same result over here. Okay, so you could imagine that in the first part of this chapter, what did you learn? If you have really keep increasing the energy, right? So you will have a curve that looks like really an ellipse, right? So really an ellipse. Maybe I'm not sure if I can draw it very well, but maybe something like this, right? So if it is really an ellipse, okay. So and in that case, that would be the situation where your harmonic potential harmonic oscillator approximation to become not good anymore, right? So because in this case, because I'm really assuming that the harmonic potential is a symmetric, right? So that is this little part here, the length, the distance of this little part here is exactly the same as the distance of this little part over here, right? So if you really consider a perfect simple harmonic oscillator, but in reality, right? So if you really exactly solve out the ellipse, right? So where the oscillation amplitude is big, okay? So I'm just exaggerating, so maybe something like this. So then you can see that now, right? So the decrease in R would be this much, right? So, but the increase in R would be that much, right? So that's the exact solution. So that means that, so for the harmonic oscillator, this part has to be equals to this part, the length, okay? But in reality, it should be not the same. And that's also easy to understand from here, right? Because the approximation we are making, right, as I draw already, right, so is a harmonic potential well like this. But in reality, right, so you can see that this part is not the same as this part. Right? So in fact, you can see that this is, we call this the anharmonic potential. Right? So that means this is not the symmetric harmonic potential. Okay. So let me just finish this slide over here also. Okay, so here I have the oscillation period to be exactly the same as the orbital period. Okay. And that's what happened for 1 over R squared. Okay. But in general, so more interesting looking orbits can be found. Okay, so if we consider other kind of forces, so where the oscillation frequency is not the same as the orbital frequency. Okay, so here I consider R to the n, right? So again, any n. Okay. So and remember, the second order derivative looks like this, and I can simplify it. Okay, so and I'll be able to say that, so this one is my spring constant, right? And then using the square root of the second order derivative divided by m, I will say that this is the oscillation frequency. Okay. So now let's also look at the orbital frequency, right? So the orbital frequency, just using the circular motion equation, right? So you'll be able to find that the orbital frequency is given by this. Okay. So here, clearly you can see that this can be different from this. So in the previous case, we have n equals 2. Then 3 minus 2 is exactly 1. So that's why this one is exactly equals to this one. But then if you pick other n, right? So then clearly the oscillation frequency not the same as orbital frequency. And if you actually look at the, you can try to look at the ratio, right? So you look at the ratio, it is the square root of 3 minus n. So, and this one more time tells you that n has to be smaller than 3, right? So if you have this 3 minus n to be smaller than 0, then you don't have a real oscillation frequency, and that corresponding to unstable orbit, right? So this is the ratio 3 minus n. And if you pick n, some particular n, okay, so you will be able to get this square root to be just an integer, okay, or just a rational number. You'll be able to do that. Just pick the n appropriately. And if that happens, okay, so the orbit will look something like this. Okay, so it looks much more interesting than what we have just here. So don't worry too much about it. That won't be in the homework or exam, but just want to show you that the behavior of the orbit can be looking something like this. You can follow one of this curve over here, right? So getting bigger, smaller, bigger, smaller. And if I plot more period, okay, you will find that the pattern repeat themselves. Okay. And well, if this number is not a rational number, then actually the patterns will never repeat themselves. Okay. But here, the two cases, I pick these two values of n, and if you try to plug it in to this, you'll find that this is a rational number. Okay. And this case, right? So indeed, eventually, the period will repeat themselves. Okay. So I just didn't plot more period to show you that. Okay. So this is just kind of for fun. And next time I will finish 2 more examples. Okay. So and then we'll go to the next part of the chapter. Okay, which is the scattering problem.